So let's continue. Now we're going to see a connection between a line integral and a double integral. With actually having the properties that satisfy a theorem, we're going to introduce Green's theorem. So this is our objective. Objective is connection between a line integral to double integral. Of course, we need some conditions here, and we call that Green's theorem. So let us write down Green's theorem and go over some examples to feel comfortable about this theorem. So Green's theorem says we start by having a curve. Let C be a positively oriented a smooth curve. So far, we know that our curve C is positively oriented and it is smooth. And at the same time, suppose C is a simple closed curve in the plane. So these are the conditions that we have for our curve C. So let us number them: positively oriented, smooth, and simple closed curve in the plane. Let G be the bounded region by curve C. So suppose you have curve C, this is your curve C, and this is the bounded region by curve C, which we call D. This is your bounded region. If P and Q have continuous partial derivatives, then the line integral of P dx plus Q dy over C is nothing but the double integral. Okay, remember that when you're taking the double integral, you're working with region D. So inside the double integral, suppose you have dA dx dy or dy dx, you get partial derivative of Q with respect to x minus partial derivative of P with respect to y. So here you have a line integral and you can use a double integral technique that you learned before to find and evaluate your line integral. At the same time, if you have right-hand side, you can simplify that into a line integral if it's easy for you and you can evaluate left-hand side integral. So let me write down this theorem here for you, then go over one example to feel more comfortable about Green's theorem. So summary. Green's theorem. Let's see the positively oriented smooth and simple closed curve, and D is the region that is bounded by C. Then you have line integral over C of P dx plus Q dy can be written as double integral over region D of partial derivative of Q with respect to X minus partial derivative of P with respect to Y dA. This is the summary of Green's theorem. One example for you. This example says, well, verify Green's theorem for the line integral. Verify Green's theorem for the line integral. So the line integral given to you is integral of xy squared dx plus x dy over C, and C is unit circle oriented counterclockwise. So C is a unit circle. Very well. Let's check to see if C satisfies the condition for Green's theorem or not. So C is just a unit circle. It's positively oriented, counterclockwise. It is smooth. It means that if you just use a tangent vector at any point to this circle, we can move this without any pull, any moving away from the circle continuously. We can move this tangent vector and get back to the original point. And of course, it's a simple closed curve. Well, what is D? D is the disk or the region with C as its boundary. So this is yours. Well, okay, it satisfies the conditions. Now we can convert our line integral using a double integral. It says, hey, instead of having a line integral, you can use a double integral over D. So this is your P and this is your Q. The partial derivative of Q with respect to X is 1 minus partial derivative of P with respect to Y, 2xy dA. So dA can be dx dy or dy dx. It doesn't matter. Well, you might say, hey, I want to take this integral. You can use polar coordinates, or you can just use the region D that you have. You can write x squared plus y squared equals to 1 because you already know that it's a unit circle. X squared plus y squared is equal to 1. X r cosine theta, y r sine theta, and dA is r dr d theta. Your x is bounded between -1 and 1, and your y is bounded between minus square root of 1 minus x squared and positive 1 minus x squared. So you can write this as the integral -1 to 1, this is your x, your y, minus square root of 1 minus x squared, 1 minus x squared. And here you have 1 minus 2xy dy dx. So the inner integral is with respect to y, the outer integral is with respect to x. Here you have -1 to 1, and here the integral with respect to y, you get y minus x, y squared, negative square root of 1 minus x squared, square root of 1 minus x squared dx. There you go. So here the outer integral, -1 to 1. If I plug in square root of 1 minus x squared, square root of 1 minus x squared, minus x times 1 minus x squared, minus, now we plug in the lower bound, minus square root of 1 minus x squared, minus x, square root of 1 minus x squared dx. So if you distribute the minus sign, you get plus and plus. And we don't have any square root here. Okay, perfect. So as you can see, these two just cancel out each other. This integral can be written as -1 to 1 to square root of 1 minus x squared dx. Okay, how do you take this integral?
You just said.
So by using trig-sum, we can simplify this integral into two integral cosine squared theta d theta. Then we use half an angle, and the outcome is equal to pi. For example, this example says evaluate the integral, line integral of x to the 4th dx plus x by dy. Okay, and the information about C is given as C is the triangular curve consists of line segments from 0 to 0 to 1 and 1, sorry, 1 and 0, and then from 1 and 0 to 0 and 1, and 0 and 1 to the origin. Very well. So here you have a line integral. Your line integral can be converted into a double integral using Green's theorem. This is equivalent saying that, hey, we have a double integral over region D with boundary C, partial derivative of Q with respect to X, which is Y, minus partial derivative of P with respect to Y, which is 0 dA. So let's graph this region here quickly. 0, 0 to 1 and 0, 0 and 1, and this is our C, and this is our D. Perfect. So now here you have your y bounded between 0 and, okay, this line here, passing through these 2 points. Minus x. So 0 to 1, this is our x, and your y, get a half y squared, 0 to negative x plus 1 dx. So just plug in this guy here, you can factor out, write down a half in front of the integral, 0 to 1, and negative x plus 1 squared dx. Very well. So if we use u solve, we get negative 1 over 6, negative x plus 1 to the third, 0 to 1. And if we substitute 1, it's going to be 0. If I substitute 0, I get 1, negative 1. So it's going to be positive 1 over 6. Well, we have a formula. Now let's take a look at this formula here. So consider a vector field F, which is defined as minus y and x. Let's see be a smooth closed curve. Then the line integral over C, so note that your first component is minus y and second component is x. So the line integral of p dx plus q dy, which can be written as the double integral d of the partial derivative of q with respect to x, which is 1, minus the partial derivative of p with respect to y, another negative 1, dA, it's equal to double integral to dA over region D. Okay, so if I factor out 2, what I have here, I have the double integral over region D, dA. So what I can write is area enclosed by area enclosed by C is equal to a half line integral P dx plus Q dy. Let me write down the formula here. So area enclosed by smooth, simple curve C is a half line integral, so this is over C, line integral P dx plus Q dy. Give us an example. How do we use this formula? Well, example says, evaluate the area of x over a squared plus y over b squared equals to 1. which is an ellipse, using a line integral. So how do we do that? Well, the formula that we have says the area enclosed by a smooth simple curve C is a half line integral Q dx plus Q dy. What is P? What is Q? So remember that we defined our vector field to be negative y and x. We said that, hey, for this vector field, by using this vector field, we drive this formula. Okay, so your P is minus y, and your Q is x. Well, this is what we have, and our goal is to calculate this line integral. Isn't it easier for us to just convert x into a cosine theta and y into b sine theta? Then dx is negative a sine theta, d theta, and dy is b cosine theta, d theta. Then we can just plug them here. We can substitute all and get rid of all of x and y's. Why not? So this line integral can be written as a half integral minus y. What is y? Y is b sine theta. So minus b sine theta times dx. What is dx? Dx is negative a sine theta d theta. Plus, what is x? X is a cosine theta. A cosine theta times dy. But what is dy? B cosine theta d theta. Well, this is just elementary calculus integral, and you all know how to deal with this integral. So here you have a half integral. You get AB sine squared theta plus cosine squared theta d theta, and this is equal to 1. So you get a half integral AB d theta. So theta ranges between 0 to 2 pi. You get a half AB times 2 pi. We can cancel out 2 and 2. This is equal to AB pi. The area of an ellipse, and this is the general form of your ellipse, and this is the area enclosed by this ellipse.